In question 5a, we're asked to add to these axes to show how the radius r of a nucleus varies with its nucleon number A. Well, the radius rises rapidly at small nucleon numbers, then tailing off at larger nucleon numbers, something like this. In B part 1, we're given the radius of a gold 197 nucleus at 6.87 times 10 to the minus 15 meters. We need to show that the density is about 2.4 times 10 to the 17 kilograms per cubic meter. Well, density is mass divided by volume. The mass is the number of nucleons multiplied by the atomic mass unit U. The volume is 4/3 pi r cubed. Putting in all the values, we get a density of 2.41 times 10 to the 17 kilograms per cubic meter. We get 2.41 times 10 to the 17 kilograms per cubic meter, which is around 2.4 times 10 to the 17 as required. In part 2, using data from part B1, we need to find the radius of an aluminium 27 nucleus. Well, given that the radius is equal to the radius of one nucleon times the nucleon number to the third, we can rearrange to get the radius of one nucleon, and this is a constant, so then the radius of gold over the nucleon number of gold to a third will equal the radius of aluminium over the nucleon number of aluminium to the third. Rearranging for the radius of aluminium, putting in all the values we have, gives 3.54 times 10 to the 15 meters. In part C, we're told nuclear radii have been investigated using alpha particles and Rutherford scattering. In part C, we're asked to compare the two methods of estimating the radius of a nucleus, being electron diffraction and alpha particle scattering. Well, alpha particle scattering finds the nuclear radius based on the distance of closest approach. At this point, the initial kinetic energy of the alpha has become electrostatic potential energy. We've got the kinetic energy mv squared over 2 equaling the potential energy 1 over 4 pi epsilon naught q1 q2 over r. Electron diffraction uses the de Broglie wavelength of the electrons, the de Broglie wavelength being given by the Planck constant over the momentum. This finds the first minimum in the diffraction pattern to find the radius of the nucleus. Alpha scattering finds the distance of closest approach, which is not necessarily the actual radius. It depends on the initial kinetic energy of the alpha particles. The resolution of electron waves is limited to the wavelength of the waves. More energetic electrons have shorter wavelengths and so will have better resolution. The wavelength must, however, be similar to the atomic spacing to give maximum diffraction. Electrons, being leptons, are not affected by the strong nuclear force. Electrons, being leptons, are not affected by the strong nuclear force, whereas alpha particles, which are made up of hadrons, are affected by the strong nuclear force.